In this video, we're looking at kinematics with differential equations. Now, you might think we've already done kinematics, and that is absolutely true. We learned about these concepts, S, V, and A. S was where you was, velocity was V, and acceleration was A. The new thing in spec is this relationship here. And the other new thing in spec, which is a little bit annoying, we don't call displacement S anymore. We call it X in spec. So just watch out for that. It's a bit cheeky. Anyway, this differential equation pretty much tells you about velocities in terms of x. So usually velocity would be a function of time, and it still is technically, but it's a lot nicer sometimes to talk about velocity in terms of where you are. Now, for example, with this first example, you can imagine this as being a ball sitting on top of a hill, and it may roll left or right, right? So the x position, if x is 0, then the velocity would be 0 at that point, because the ball would be sitting on top of the hill and not really rolling if it was perfectly on top, perfectly balanced. Now, you can imagine that if x is 1 here, the ball would be sitting over here on the hill, and it would be rolling down, and probably velocity is, well, according to this equation, 4 times 1 squared, so 4. If x was 2, it would be 4 times 2 squared, so that would be 16. So you can sort of imagine that the velocity there would be getting bigger and bigger as the ball's further down the hill because it has rolled further. So rather than talking about it in terms of time, we're talking about it in terms of where it is, and then we use that to find the velocity. So it's a little bit different methods. You can see that because I got the x squared term, the velocity is always downwards, being positive in this case. It's always negative in this question. Okay, so how do we do this in practice? We use this equation. Now, I'd really like you to think about why this equation is true. So you can maybe prove that first one pretty easily and then use it to prove the second one. I will tell you at the end of the video, so keep thinking about why. But we'd like to find the acceleration. So you can use this version. So v to v dx is the acceleration. I might put the acceleration on the left there. So acceleration is the velocity, so that's 4x squared, times dv dx. So if we look at this, dv dx is 8x. Cool, yeah, done. So times 8x. So what we get is 32x cubed. So that's the acceleration. So that is sort of option 1 for solving this. Option 2 would be to use the other identity, so this one here. Acceleration is d over dx of a half v squared. So this is d over dx of a half, and the velocity is 4x squared, and I've got to square that. So that's d over dx of, that would be 8x to the 4 in the brackets there. And if I differentiate that, I get 32x cubed, which gives me the same answer. So that's always a good sign. So whatever way you want to do it, we get the same solution. All right, and just before we move on to the next one, I will stress that a ball rolling down a hill might not necessarily exactly follow this equation, but that's just an analogy to hopefully help you understand the concept of velocity in terms of position rather than time. Okay, this next one that I'm doing will have an actual analogy in the real world, but we'll look at that at the end. First off, we just got to solve this equation. So we want an expression for velocity in terms of x, and we absolutely can get that. So it's probably easier to use the outside equation here. So that one and that one. And we're going to start with d over dx of a half v squared is acceleration. So that's just the outside 2 bits of that equation. So we can integrate both sides, so d over dx half v squared. Integral of acceleration. We'll put in what acceleration actually was, minus 3x. Okay, now to integrate both sides, on the left-hand side, you've got this thing, you've differentiated it, and then you've integrated it. Derivatives and integrals are almost just opposites of each other. So we literally just get back what we started with plus a constant. On the right-hand side, you've got minus 3x squared over 2, because we just integrate that normally, plus a constant. Now, I might group these all into one constant, just because we don't need two, because you could just move one over the other side. Therefore, v squared would be, and we can just double everything, so minus 3x squared plus c. C is a different constant. It is 2 lots of c1. And then we can use our initial conditions. So for our initial conditions, so it was initial, so that was t is 0. The initial position was 3 centimeters left, so x is minus 3, and the initial velocity was 2 centimeters per second right. So this was positive 2. Notice that we won't actually use t equals 0 in this equation, but we can work out what this is. So I might just start v squared is minus 3x squared plus c. So that would tell us 2 squared is minus 3 lots of minus 3 squared plus c. So that would tell me 4 is, that would be minus 27 plus c. So c is 31. So we can go v squared is minus 3x squared plus 31. Just like that. And we've got our equation. Now, find the speed when x is 1. So we'll just start with our equation. And when x equals 1, we've got velocity is minus 3 lots of 1 squared plus 31. Minus 3 plus 31, so the velocity squared is 28. So that would tell me that the velocity is root 28 with a plus or minus. Okay, we're in centimeters per second for this question. So we better get an approximate for that. So root 28 is 5.29. All right, beautiful. And that's also got a plus or minus. And now, actually can't tell whether it's plus or minus, but the question's asking for the speed. So the speed roughly equals 5.29. It's the positive version. Okay. Speed is always positive. Velocity can be positive or negative, depending whether we're moving left or right. Okay, continuing from question 2, find the maximum and minimum speeds. So this is a bit of a tricky one for this, but we can do it. V squared is, and I'll just rewrite it into 31 take 3x squared. Now, really importantly, v squared is always positive and x squared is always positive. So we can never get negatives, but can we get velocity equals 0? Because that would really be the minimum if we can make that happen. And the answer is yes. So if we pick, well, if we try and make the velocity equal 0, so 0 squared would have to be 31 take 3x squared. So 3x squared would equal 31. So x squared is 31 over 3. Therefore, x would have to be plus or minus root 31 over 3. And we can get an approximate for that, 31 over 3. So that's not very helpful. 3.21 plus or minus 3.21 centimeters there. So that's the maximum. Now, the minimum velocity. So that would give you velocity is 0. Now, for the maximum, well, can I make the velocity as big as possible? So this is always 31 take a positive number. So maybe I will try and make it 31 take 0. So this would happen when x is 0. So v squared is 31 take 3 lots of 0 squared, which is 31. And then v would be root 31 with a plus or minus, and we can get an approximate for that. So root 31, 5.57, roughly. So therefore, centimeters per second, and we should have units there as well. So speed would be 5.57 centimeters per second. All right. All right, now I've also sort of graphed this. Instead of y, I'm using the velocity, and x is the displacement. So the velocity would be in centimeters per second here, and the x would be in centimeters as displacement. Very weird graph. First of all, y would have to be greater than or equal to 0. Actually, no, it doesn't necessarily. But we can see what the maximum is. So the highest point here is that number we just found, 5.56, when the displacement was 0. And then the minimum speeds were 0. You can go down to negative 5.56. So we sort of got this thing that's going positive velocity, negative velocity, positive velocity, negative velocity as it goes around. I would encourage you to pause the video and maybe think about what a real world example is of something that does that. Hopefully you've done that. This is a pendulum. So we have this pendulum swinging like left and right. X is just the horizontal position. And you can think of when x is 0, this is right in the center. And when x is 0, the velocity is at its biggest, so plus or minus 5.57 centimeters per second. I'm hoping that makes sense, because if I sort of, swing this pendulum back and forth, when's it going to be going the fastest? Well, right when it's going past the center again. And the pendulum seems to swing out to 3.21 centimeters, and that's when the velocity is 0. And if we look here at minus 3.21 centimeters, the velocity is 0 again. Well, I'm also hoping that makes sense, because if the pendulum's swinging back and forth, then at these endpoints, you're going to get the velocity 0, because that's where it's turning around. The other point that we found was when x is 1, the speed was 5.29. So I might just pop that on our little graph. X is 1. And at that point there, the velocity is 5.29. Yeah, it's going to be a plus or minus, because it could be at x is 1 coming back. That would be negative, or it could be coming back to the right, which would be positive. So we actually don't know which one it is, but I do know the speed is 5.29 centimeters per second. So if you're familiar with pendulums, you might actually expect that x is some trig function in terms of time, and that's absolutely true, and we'll look at that in the next video. But the beautiful thing about this is, look at how simple that equation is. Acceleration is minus 3x, that's it. And apparently, if you solve that equation, you get like trig, which is sines and causes and stuff. And that's why we really care about learning trig, because trig itself is a complex concept that it seems like somebody came up with it. It's like, yeah, cool, let's just do that for fun. But where it comes from is really simple differential equations like this, and that's why trig shows up everywhere. All right, now as promised before, I'll just explain why this identity is actually true. Now, x was your position. The velocity is defined as the derivative of position with respect to time, dx dt, and acceleration is dv dt. So those are the tools that you'll need if you want to try and prove this. I would encourage you to do it, so pause the video now if you want to give that a go. I'm going to start from the left-hand side. So half v squared, and we're differentiating this with respect to x. So what that gives you is, well, you got 2 lots of a half v, so you just do the normal derivative. So in other words, that's just v. And then you've got to differentiate with respect to v, so dv dx. So almost as a one-line proof, just using implicit differentiation, that first pair is true. And then v is dx dt. So what we're going to do is replace v with dx dt there, and this is still dv dx. Now, the way that derivatives work like this is, it doesn't exactly mean this, but you can sort of think of it like the dx's cancel. So what you're left with is dv dt, which is acceleration. So that's how you prove that identity there.